All right, we're going to look at logarithm functions and their graphs. And the definition of a log is if y equals log base a of x, if and only if x equals a to the y. Okay, this is an important definition. This is going to help us throughout our studies in the next two sections, logarithms and natural logs. You should be able to go between log form and exponential form. All right? So first thing we're going to do is evaluate the following logarithmic function for the given value of x. So they want us to find f of 16, which is log base 4 of 16. And what we can do is we're looking for the y value, right? We can apply this definition. 4 raised to what power equals 16? I apply the definition. I remember the definition by it's the base. This is also called the base. Raised to this power equals this. I just add this little pattern that I do. That's how I remember the definition. So 4 raised to what power gives you 16? Well, 4 squared is 16. So what's y value when x is 1? So 5 raised to what power? 5 to this power equals 1. 0. Remember the definition from Algebra 2. So 3 raised to what power equals 81? 3 times 3 is 9, times 3 is 27. 27 times 3 is 81, so it's 4. Okay, y equals log base 2 of 1/4. So 2 raised to 1 power, 2 raised to what power equals 1/4? Negative 2. Because it's 4 is 2 squared. Questions here? All right. Common log is when the log is base 10. And common logs are written as log of x. When there's no base with the log, it's an implied base 10. All right? So if f of x equals log of x, evaluate this function. So they want us to find log of 2.5. Here's where the calculator can be used. Because on the calculator, there is a log button. It's right next to the 7. There's a natural log button. We'll get the natural log tomorrow. But that log button it's implied 10. Calculator can't do all those different bases, so the calculator is just base 10. So if it's a base 10 and they want you to find log of 2.5, all you have to do is put that into your calculator. Log of 2.5, which is about 30.3979, something approximately. So 10 to raise to this power, yep. 10 raised to 0.3979. You can't see that. There's my log of 2.5. If I take 10 and raise it to 2.499, or I'm sorry, take 10 raised to 0.3979, you get 2.499. If I would have went 10 up arrow this number, I actually get 2.5. So yes, that's what that means. Okay. What about this one? Log of -2.
It's going to be an imaginary number.
Why?
Because you can have the power of 10 be a negative.
10 raised to what power equals a -2? Well, 10 raised to any power is going to be what? Positive. So this is a no solution, undefined. And if you look up at the definition, for x greater than 0 and a greater than 0. So the bases and the x, these both have to be a positive number. They cannot be 0. They cannot be negative. Okay? You can't take the log of any negative number. And you'll never see a base of a negative number. And then the last one, what's the log of 4/5? Log of 4/5 for 0.8. I got a negative 0.0969. Is that what you guys got?
Yep.
Questions there? All right. Then we're going to go back and look at those rules. Do you remember your log rules? All right. Log of any base of 1. Anytime you do the log base A of 1, it's always 0 because A raised to the 0 power equals 1. It's the only way you get 1. Any number raised to 0 power is 1. So log base A of 0, log base A of 1 is 0. Log base A of A is 1. Because A raised to what power equals A? That's a 1. if it's log base a of a to the x, it equals x. Because a raised to what power equals a to the x. And then here's, I like this one too. If you have a raised to the log base a of x, you also get x. And for these two rules, if I see a log and I see these two bases are the same, I think to myself, oh, they cancel out, so I get x. Here, I have an a raised to the log of the same base. They're going to cancel each other out and get x. And then we have that one-to-one property like we had yesterday, that if I'm taking the log base a of an algebraic expression, it equals log base a of another algebraic expression, then those two algebraic expressions are equal. So let's look at these rules and apply them. Okay, number 6, simplify the following expressions. We've got log base phi of 1, what's it equal? Any log of 1 equals 0. That's a rule. Log base 6 of 6, whatever the exponent is, which is 1. 8 raised to the log base 8 of 30. It's 30. Again, here's where this base and this base are equals. They count. I think to myself, they cancel each other out. Log base 3, 3 to the 4th, 4. How many? Yes.
If you had log base 1 of 1, could it be 0 or 1?
Log base 1 of 1. That's 1. 1 to what?
Just like last year.
Really, Charlie?
Just like last year, algebra 2.
Yes, he asked the hardest question.
He tried to break them up.
Huh.
Zero divided by 0.
Well, what I think is 1 raised to what power equals 1.
Can you move it over?
But 1 is 0 power is 0 or 1.
So can it be 0 or 1?
Both.
This would be like log base 10 of 10. That's going to be 1.
Didn't you say they could cancel out?
They do, and it gives you the exponent.
Okay. So,
But then she also just said if it's
That's a
the
good
one-
question. Save that question for tomorrow, and we'll ask Linda tomorrow. And we'll look it up also. Log base 1 of 1. Is it 1, or is it 0, or is it both?
Infinity. Somehow.
Never been asked that question.
Good job, Charlie.
All right. Did you ask that question last year? Why not?
that didn't come up.
All right. 10, 11, 12, and 13 are all that one-to-one property. Log base 5 of y equals log base 5 of 16. So what do you know? Y equals 16. So for number 11, what base is there? 10. So log base 10 of 4 minus 3x equals log base 10 of x plus 2. So 4 minus 3x equals x plus 2. So 4x equals 2. X equals 1/2, ladies and gentlemen, not 2. Some people will give me an answer 2. You have to divide by 4. questions on 10 or 11? Bases are the same, so x squared plus 4 equals 29. X squared equals 25. So x equals plus or minus 5. Bases are the same, so x plus 4 equals 4, so x equals 0.
Will it always be this? Will it get more complex?
I think they're all easy. To me, I think it's fairly easy. I think the students, where the students struggle, is applying some of the rules
Yeah.
and graphing them.
Okay.
And I don't even. Oh yeah, we'll get into some of the other rules here. So, all right. Next thing we're going to do is we're going to graph these. Sketch the graph of f of x equals 2 and g of x equals 2 base x. This one we did yesterday, right? So we had 1, 2, negative 1 was a half, and it went like this, and it approached. And I'm just going to say from 3.1 notes. If you weren't here yesterday, make sure you go watch that video. So y equals log base 2 of x is what we're going to graph next. I'm going to write this using its definition. Its definition says 2 raised to the y power equals x. What'd you ask? Does it just flip the points?
But when you have
I never thought of it this way. But what happened between the two? The x and the y's are flipped. So let's find out. How I do it was, instead of picking x values, I pick y's. So I'm going to use negative 1, 0, 1, and 2. So when I let y be negative 1, what's x? 1/2. When I let y be 0, what's x? 1. When I let y be 1, what's x? 2, 4. And as you can see, yes, the points are just flipped. So I go over a half, down 1, 1, 0, 2, 1, 4, 2. And if we just flip the order pairs, what can we say about these two functions? They're inverse of each other. And we talked about inverse functions already And you can see inverse functions are reflected about the y equals x graph, and are these two reflected about the y equals x graph? Yes, they are. So Mason gets an A+ for the day because before I even got to get into inverses and flipping the order pairs, he saw it.
Good job, Mason.
This time, thanks, Charlie. Appreciate it.
All right, find the domain, x-intercepts, vertices, asymptotes of the following. Sketch the graph. Well, let's do, this is base 10. So 10 to the y power equals x over 4.
You move there.
So for the domain, what do we know has to happen with that x over 4? It has to be what? It has to be greater than 0. So x has to be greater than 0. So there's our domain. Our x-intercept is found where?
Plug in 0 for y.
Plug in 0 for y. So I'm using the definition. So 10 to the first power is 1. So x is 4. So I have an x-intercept of 4. What happens when y is, we already got y is 0. What happens when y is 1? What's x? 40. So clear out over here somewhere we get to 1. What happens at negative 1? Y. All right, so what happens when x is negative 1? Or y, I'm sorry, is negative 1? We get 1/10 equals x over 4. So when x is negative 1, or when y is negative 1, we get 2/5. So 2/5 negative 1. Y again. The y values are going to be negative. We're never going to cross it. So we have a vertical asymptote at x equals 0. X will never be 0. Questions there? This one will be similar. We're going to just skip it since we had a 2-hour delay. Here are some basic characteristics of a logarithmic graph. the domain, this is just a basic, this is a parent function. The domain is going to be 0 to infinity. Range will be negative infinity to infinity. X-intercept will be 1, 0. It's increasing. It will have an inverse. Y-axis is a vertical asymptote. It's going to be continuous. And it's going to be the reflection of y equals a of x over the y equals x. Okay, that's what we just looked at. So describe the transformation. So we're looking at log base 3. What does that negative 1 do with this function?
Move down.
Down 1. What does the 2 do? Left 2. Right 1. Up 3. Is that it? We got this negative in front of it. What's that do? So it reflects over x. So again, nothing different about transformations here than what we had yesterday or what we had on our polynomial functions, our quadratics, our x cubes, our absolute values, square roots. Okay, transformations are still the same. Questions? Then we've got the natural log function. The natural log function is just the log function base e, and there's a special point, there's a natural log right here on the calculator. You can't see where I'm pointing. It's right underneath the log. And so for 1920, we're just going to evaluate. You're going to put those into your calculator. So you're going to take the natural log of 4. Over here, you're going to take the natural log of 3.8 plus the square root of 2. So what do you get for 19? What do you get for number 20? Be careful on problems like this. You're only taking the natural log of x. Then you're adding the square root of 2. 2.749. Then simplify. Well, natural log, this is like a base e. So what does ln of e to the 1/3 equal? It's the base e, so it's just 1/3. What's, yes, it's just like log base e of e to the 1/3. Natural log of 1?
0.
0, and what's 15 times 0? 0. What's the natural log of e? And it gives us 1. Natural log of e. Log of e is 1. Just like log base 10, log base a of a was 1. And then for the domain, again, just like the log, you cannot take the natural log of a negative number. It has to be greater than 0. So x plus 3 is greater than 0. So x is greater than negative 3. If you write it in interval notation, it'll be negative 3, comma, infinity with parentheses. It's probably how it's written on your answer sheet for your homework. For this one here, 3 minus x has to be greater than 0. So 3 must be greater than x. So x is less than 3. So that's negative infinity to 3. It's backwards.
Does it matter if you put the 3 before the negative infinity?
Yes, it does. You always put the smallest number first, then the largest. Your infinity, your negative infinities will either be your first, negative infinity will always be your first one, positive infinity will always be your last one. And then for this one, x cubed has to be greater than 0, so x has to be greater than 0. Do you guys remember, because I'm using them here, ln of x to the third. Do you remember about that exponent, what you could do to simplify these, the natural logs and the logs? What can you do with that exponent? You can bring it, the exponents can come in front for natural log and logs. It's one of those rules from Algebra 2. So it's just 0 to infinity. Questions?